Continuing with our discussion of polar functions, we're now going to bring calculus to the table. We're going to talk about how we find the area of curved regions. Most particularly, we're going to talk about finding the area. I can get this to work right here. We want the area of a polar region. The area of a polar region. Now, just as a review, we all know this, but just as a review, previously we have found areas of curved regions in the plane by using areas of rectangles. Our rectangles don't even have to be, all the same width, or they're definitely not the same height. And we used the definite integral, remember, from A up to B, and that was instructions that said add infinitely many. Now, for us, for what we did last fall, it was add infinitely many areas of rectangles, but we have seen that doesn't really even have to be areas of rectangles. We can add infinitely many line segments and find length of a curve in a plane. Now, for our polar regions, we're going to use sectors. Remember, a sector is a portion of a circle. Let's talk about this shaded region right here, this gray area, and that's angle measure theta. Remember, any point from the center of a circle to the surface of the circle, the distance between those 2 points is the radius of the circle, so that's where r comes from. We know from geometry that the area of any circle is pi r squared based on the measure of the radius. And so we remember, hopefully from geometry, that if we were going to find the area of any sector, we took the portion of the whole circle, which is what this factor here represents. If theta is a smaller measure than one entire revolution, which is 2 pi, then theta divided by 2 pi is the portion of the circle that we're talking about. And that portion of the circle we're going to multiply by the area of the entire circle. So the area of any one sector in a circle was theta over 2 pi times the area of the whole circle, pi r squared. This cleans up quite nicely. We can see our pi's cancel. We'll put our theta times theta out here after r squared, and so we have 1/2 r squared theta. So this is the area of a sector of a circle. Area of a sector of a circle. And we know that on our polar regions, everything is based on r and theta. We have some function r, which is a function of theta. We have limacons and roses. R equals a plus or minus b, either sine or cosine theta. R equals a times the sine or cosine of n theta for our roses. So if we added up infinitely many sectors and we had the change in our theta be super, super tiny, like on our rectangles, we said the widths of our rectangles are tiny changes along our axis. For us, most of the time last fall, it was, well, all of the time last fall, it was changes along the horizontal axis, but we saw earlier in the lessons that we just did that we can have changes along the y-axis as well. So tiny changes in theta, in our angle measure, lead us to really tiny sectors of our circle, really tiny changes in the area. And if we added infinitely many of those, remember the definite integral? This says add infinitely many. So if we add infinitely many little areas of sectors, which we just discovered on the last slide, that's what this represents. And we don't have from A up to B in this context, we have from alpha to beta, because our independent variable is an angle measure. So you'll see alpha to beta in this context instead of A up to B. But it's still representing the lower limit of integration and the upper limit of integration. So here's the formula that we're going to use. The formula for area of a polar region. Formula must be memorized. You have to know this formula. The biggest problem here is students forget this. They always seem to remember r squared d theta, but they forget the 1/2. We usually write the 1/2 out front. We have 1/2 the integral from alpha to beta r squared d theta. And we'll be given, remember, we're going to be given r, which is a function of theta. So r is going to be easy to find. We're generally going to be given r. Alpha and beta are going to be the biggest wild cards for us. They're fairly easy when it comes to limacons. They're a little more challenging when it comes to roses. But we're adding up infinitely many areas of sectors, and that's going to give us the area of a polar region. So let's look at an example. Find the area that's enclosed by r equals 2 times the quantity 1 plus cosine theta. This is a limacon. Well, I know it's a limacon because of the form of it. It is definitely a plus b cosine theta. It's specifically where a equals b, so this is a cardioid, just to practice what we did on the last lesson. So we have a cardioid. We could draw a picture of it if we wanted to, but in this context we don't need to. It says find the area of the enclosed. So my formula again is 1/2 alpha to beta r squared d theta. So I'm just going to fill in the pieces that I have here. We'll come back to alpha and beta. I know what r is. R is 2 plus 2 cosine theta quantity squared d theta. See how that part's really easy. The r squared part's really easy because they give you r. Now, the alpha and beta part are a little bit different. Here's why we like limacons. If they want, and this needs to go in your notes, if finding the entire area, meaning they don't just want the upper half of the limacon or the lower half of the limacon, they don't want the loop of the limacon. If they want the entire area of a limacon, then your limits of integration are always, and I mean always, so then we always use 0 to 2 pi. It's going to take the entire full rotation of a circle from 0 to 2 pi for our theta measure to actually map out that entire limacon. So when we have a limacon, and that's why it's just as important for us to recognize the form of a limacon, because this is not going to be true for roses. So on a limacon, we really don't even need our calculator. We can do this by hand. Now we're down to what we already know. So let's multiply things out here. You're going to have to FOIL this out. You have one term plus another term, and that's being multiplied by itself. So first is 4. Outside is 4 cosine theta. Inside is 4 more cosine theta. So that's 8 cosine thetas. And last is 4 cosine squared of theta. And that's all with respect to theta. So this is fairly easy for us to do. We know how to do this. We know how to do this. This is the only issue that we're going to have because, remember, integrals break up over plus signs. So we know how to integrate 4 with respect to theta. We know how to integrate 8 cosine of theta with respect to theta. But we don't know how to integrate cosine squared of theta. And I don't know if you remember, but I said last fall there would be 2 more trig identities that I would give you in the spring semester that you would have to know. And here they are. And this is the reason why we need these 2 trig identities, because then they give us a form where we can actually integrate. So if this is an identity, this means equal. Remember the power of that symbol right there. Anytime I see cosine squared of theta, I can write this instead. And since I can do that, then I can put it in a form where I actually can integrate what's going on. So this is 4 plus 8 cosine theta plus 4, and now I'm going to substitute this in. I am going to factor a 1/2 out front. I'm going to rewrite this as 1/2 times 1 plus cosine of 2 theta. I think that would be easier. 1 plus cosine of 2 theta. Now this isn't cosine squared of theta. This is cosine of 2 theta. That's a double angle measure. All right, d theta. So we're in good shape here. We'll clean it up a little bit before we actually start integrating. So I'm going to come over here and copy it down here. 1/2 0 to 2 pi. I have 4 plus 8 cosine theta. And now 4 times 1/2 just gives me 2, plus 2 times the quantity 1 plus cosine of 2 theta. It seems like there's a lot going on here, but there's really not. I'm not making that many changes. I just made a trig substitution here. Now I distributed my 4, and now I'm fixing to distribute that 2, and then I'll gather like terms. So it looks like there's a lot going on here, but everything going on right now is algebra. Everything in the next couple of steps is just going to be algebra. Now I'm going to distribute this 2 through this parenthesis, so that's plus 2 cosine of the double angle measure, d theta. Now I have common terms that I'm going to put together here. All right, so now I have 1/2 the integral from 0 to 2 pi, and 4 plus 2 is 6, so I have 6 plus 8 cosine theta plus 2 cosine of the double angle 2 theta d theta. Now I have everything ready. I'm ready to actually find my antiderivative and then do fundamental theorem. So let's see, I'll take a couple more steps and I'll probably wait to finish it for the next video. So let's find our antiderivative. So I'm going to pop my 1/2 out front. The antiderivative of 6 with respect to theta is 6 theta. And I'm going to copy this plus sign down. I'm going to pop my coefficient out front. What did I take the derivative of to get positive cosine of theta? Well, that was the derivative of positive sine of theta. Watch those positive and negative signs. Those are really important here. All right, I'm going to copy this plus sign down. I'm going to pop my coefficient out in front of the term. And now I'm down to finding the antiderivative of this term. Well, this is a u substitution. Something has been put into a function machine. 2 theta was put into the cosine function machine. So this is a u substitution. So if u is 2 theta, then du is 2 d theta. So for this term, just for this term, I'm off by a constant, 1/2. So I'm going to come out and I'm just going to work on this term right here. I have everything copied down. I'm going to do the work it takes to find the antiderivative and then write the antiderivative right there. So I have now 1/2 the integral. I'm not messing with this 2. This 2's right there. I'm just messing with the cosine of 2 theta. So 1/2, I'm off by 1/2, the integral of cosine u du. See how this is the u substitution, the indefinite integral u substitution for just that term right there in between the brackets. So be very meticulous and very careful when you find these antiderivatives. So the antiderivative of this indefinite integral is 1/2 the sine of u plus c. So I can write that right here. That's 1/2 the sine of, and we said u was 2 theta. And now I'm not going to write the plus c. Remember, we used the indefinite integral to find the definite integral. So I'm going to stop this video right here, and we'll pick up and do fundamental theorem on the next video.